So in the equatorial region, that's where the sun's radiation is more concentrated, that increased radiation at the surface, leading to warmer, less dense air rising. That less dense air exerts less surface pressure, so we have low pressure in the equatorial region. Lifting air, moisture-rich air, lots of moisture in the area, and so the sunlight leads to the evaporation. The winds are converging at this point because that lifting air, that idea of nature abhorring a vacuum, air rushing in, being part of the lift cycle of the Hadley cell, that lifting warm, moist air leading to high precipitation in the region. So we have the surface winds converging, leading to a rising moist air, leading to heavy precipitation in the equatorial low. Then, as part of the Hadley cycle, that air cools, descends further south in our case, or north. It's mirrored, so we can talk just about the south in our case, descending around 30 degrees latitude, creating a high pressure. Now, what's happening there is the air is cooled, become more dense, and so it's sinking. That sinking air, when it encounters the ground, exerts a higher surface pressure, but that air is also devoid of moisture, having lost most of it in the equatorial region, and the heavy precipitation that characterizes the equatorial region. So, if the subtropical highs, you have when the descending air column meets the surface, the winds diverge. So the subtropical highs occur about 30 degrees north and south of the equator. That is the descending arm of the Hadley cell. In our case, it's the southernmost part of the Hadley cycle cell here, and it's called the Subtropical Ridge. You've got the cool, dry air creating a high pressure band in that area. Most of the moisture, as I said, in the air has been lost in the equatorial region. So it's no surprise then for a lot of these areas where you find the subtropical highs, you also find major deserts. We'll see that in a sec. But it's where the trade winds and westerlies originate. We'll talk about them later on. In the equatorial region, it has a special, part of it has a special name. It's the Intertropical Convergence Zone, and we'll describe that in a minute. But it's also known mostly by sailors, I guess, as the doldrums. I think it originated with the early, the age of sail explorers in the region, referring to the tropics as the doldrums. That's because what you have there is you've got that warm, moist air, high convection, so the convective heating from the sun, leading to that less dense air rising, bringing moisture with it, forming cumulus clouds, and sometimes even strong enough to form the cumulonimbus clouds or thunderstorm clouds. But that pressure belt, that less dense air, is quite expansive. It's a wide band of low pressure. So in that area, you don't have the pressure gradient force as strong as other areas. So there's light winds. And so that idea of sailing boats, waiting for that wind that will save them, often if people are down in the doldrums, they're I don't know, they're not going anywhere. They feel like they're stuck. So that's kind of where that term originated. But the idea is that you've got a wide band of low pressure, very little winds crossing the equatorial low. But it is where the trade winds meet, and we'll describe them later. So we talked about this idea of the subtropical ridge. We're going a little bit further here. The subtropical ridge, again, it's mirrored in the northern hemisphere, so we can just focus on the southern hemisphere. So in this case, we have the Hadley cell starting at the equator, that low pressure, less dense air, moisture laden, losing most of its moisture, cooling, and then descending here as part of the Hadley cycle. So it's on the northern side, it's the Hadley cell. On the southern side is the Ferrel cell, meeting at about 30 degrees in latitude. So you're moisture depleted, you're cool air, so you're descending because you're more dense rather, and you're creating a high surface pressure. And when those winds hit the surface, they diverge. So it's a high pressure area. It's cool and dry. and leads to stable atmosphere that we enjoy sunny skies in winter because of the subtropical ridge being around the middle of Australia. And so that moisture depleted column of descending cool air, not surprising then that you've got most of the deserts around the world at the plus or minus 30 degrees latitude. The subtropical ridge is a major driver for Australian weather. In fact, it characterises our winters. We have beautiful blue skies across Australia on many a winter day, purely because in winter the high is is around the middle of Australia. You'll recall from last week's prac, the sun moves in the sky north and south of the equator, and in winter it's further north in the sky. So those highs will be further north. In this case, the subtropical ridge will be through the centre of Australia. This is winter on the right-hand side. In summer, the subtropical ridge is further south. With the sun, we're facing the sun more in the southern hemisphere during our summers, and the subtropical ridge therefore will be further south. Where these high pressure belts are relative to the Australian landmass will result in the weathers we have. And we will talk about them in another lecture and the impact on some of Australia's key weather. Again, from last week's tutorial, we encountered this idea that's the tilt of the Earth's rotation, axis of rotation, and as the Earth orbits the Sun, creates the seasons. So that means that we get a north-south migration of the suns across the sky, and that leads to warmer or cooler air temperatures. And this is, in this case, we're just focusing on the equatorial, that intense heating from the sun, that band of heating moving south in summer, then back up to the north in our winter, northern hemisphere summer. So that migration of that heating north and south of the equator drives our circulation patterns. And this one is what we'll call the Intertropical Convergence Zone. It's also known as Earth's thermal equator. It's the path of the intense heating north and south of the equator. Note that it follows the landmass. This is because land can heat up a lot quicker than oceans, and it sort of tends to, as the sun goes north of the equator at its maximum of the Tropic of Cancer, heats up this region a lot more intensely. The heat sticks around, and so you get the low pressure system focusing here. In the reverse, in the southern hemisphere, during our summers, that low pressure, that intense heating comes further south, and so you find that the path of the Intertropical Convergence Zone will follow the greater landmass. High temperature, high convection, greater convergence. We'll talk a bit more about that later on, and particularly the patterns of winds. But in that equatorial region, the tropics, you'll find that intense heating leads to a lot more moisture in the atmosphere. So here we have an animation of modeled and observed moisture in the atmosphere, what we call precipitable water. It's the amount of water vapor content in a column of atmosphere. And what you can see here in those red colors is a high concentration around the equator. And as you move away from the equator, those greens into blues colors, the moisture content of the atmosphere decreasing. What this says is that the heating falls north and south. So, sorry, the heating band moves north and south, and with it moves the moisture up and down. So a lot more moisture available to make rainfall in the tropics. What does this mean, however, for the region? the movement of the intertropical convergence zone north and south of the equator brings a very important weather system to both northern Australia and to places like India and Southeast Asia. These are the monsoon winds. Monsoon being a word, I can't remember which word, I can't remember the origin, but for seasonal winds. So you got this warm, moist air. In December, January, February, the intertropical convergence zone is south of the equator. And so what we have, and we can talk about how these wind patterns come about, but effectively the intertropical convergence zone is where these winds meet to form that convective area, that large convection, moisture-rich environment, lots of precipitation. In December, January, February, we get a lot of rain in northern Australia. In June, July, and August, that rain, that the intertropical convergence zone has gone further north. So the convergence of winds, moisture-rich air coming over India, for example. Here's just an example of the amount of rain that fell in the space of a week in India as a result of monsoon. So we're getting up to about a metre, well, 700 millimetres of rain falling in a week across this part of the west coast of India due to the monsoon winds coming up from the Indian Ocean. But how these patterns originate, we need to learn about Coriolis, and that's another part of the lecture. Oh, here we go. So we recall that we have air movement from high pressure systems to low pressure systems. The Hadley cell, or Hadley, proposed a single cell model to describe the flow of air along the surface from high to low. We don't see that in practice. What we see is something more like the 3-cell model. In fact, the 3-cell model, I think, is the established representation of the major circulation patterns in the Earth's atmosphere. So what we see is these series of highs and lows at different equatorial bands. The high, the low pressure system here in the equator, we understand it's that intense heating in the sun, less dense air, less pressure at the surface, rising air column. But then we've got the descending arm around the of the Hadley cell around 30 degrees. And so we see wind patterns that converge and move westward at the equatorial low and deflecting this way. Now, what gives rise to the motion we see? It's this Coriolis force. It's a fictitious force. And for this, I'm going to get you to imagine you're driving along. You've got your sunglasses resting on the dashboard. And as you round a bend, you feel a force, or rather your glasses will feel a force going in the opposite direction to where you're turning. This is a fictional force called centrifugal force. Moves them, if you're turning to the right, it moves the glasses to the left. Thing is, there is no force pushing those glasses to the left. The glasses wanted to stay still. What's different here is that your car's turned right. The glasses wanted to keep going straight, but you moved the environment to the right. So it appears that the glasses move left. So this is what we call the effect of inertia in response to the centripetal force. The centripetal force is moving the car to the right. The car is a non-inertial frame of reference. And so that's exactly what we have on Earth. We have a rotating Earth. Rotating Earth is a non-inertial frame of reference, just like the interior of the car. So one principle to recognize here is that the Earth spins faster at the equator than at the poles. So as you move away from the equator, the rotation of the Earth stays the same. Right? The Earth spins around once every 24 hours. But in terms of distance over time, the equator speed is a lot faster to get that. So there's a lot more mass, if you like, that's got to make its way around the Earth in 24 hours at the equator than as you move away from the equator. So the Earth spins faster at the equator than at the poles. And so that means then if you're at the equator, and you fire north or south, consider this picture here on the left, and firing a cannonball or throwing a ball to a mate standing north of you. You expect the ball to just travel straight up to where your mate is if he's right in front of you. What actually happens, because you're going faster at the equator than he is at a higher latitude, the ball has a tangential acceleration speed in the direction of rotation that is that's faster than your mate is experiencing, and so the ball will actually move to the right, or look like it's moving to the right. And so deflection in the northern hemisphere from a straight line path is to the right. In the south, it's to the left. Same principle though. You're throwing a ball to your friend who's further south than you. You're going faster at the equator than he is at the further south. Therefore, the ball will end up more around to the east than he is. So deflection in the south is to the left. I like to think of it as we drive in the left in Australia. We're in the southern hemisphere. Deflection is to the left. And in the north, it's the opposite.